Next we will have Brandon Augustino and Jiaqi Leng, who will present to us a quantum central path algorithm for linear optimization.
Thank you for the very nice introduction. My name is Brandon Augustino. I'm with the Global Technology Applied Research Group at JPMorgan Chase. Delighted to be presenting this work with my co-author, Jiaqi Leng, who's a postdoctoral fellow with the Simons Institute for the Theory of Computing at UC Berkeley. The title of our talk is a quantum central path algorithm for linear optimization, and this is based on joint work with Giacomo Nannicini, Tamás, Terlaky, and Xiaodi Wu. Okay, so as the title suggests, we're going to be looking at linear optimization problems, which are perhaps the most well-studied class of constrained convex optimization problems due to the simplicity that they exhibit and the fact that they're readily able to model fundamental applications across a number of scientific domains. The best performing algorithms in theory and practice for this class of problems are interior point methods, which have been known to be able to solve a linear optimization problem in polynomial time since 1984, when Karl gave his seminal result. Since then, there's been a vast interest in studying interior point methods, not just for linear optimization, but broad classes such as second-order conic optimization, semi-definite optimization, and today, the best IPMs for linear optimization can solve these problems in matrix multiplication time. Now, given that they work so well in both theory and practice, there's of course a natural question as to whether or not quantum computing can help accelerate the IPM framework. And this is largely motivated by the fact that in each iteration of an interior point method, you're solving a large, dense system of linear equations. And so there was a natural idea explored by Karanidis and Prakash a couple of years ago, which was simply, okay, the classical solution of a large linear system is our bottleneck. Why don't we try to accelerate that with the use of a quantum linear systems algorithm? The challenge is, of course, when I use the quantum linear systems algorithm to solve the Newton linear system, I'm not actually getting my search direction or my Newton step. I'm preparing a quantum state and coding the step. So I have to perform quantum state tomography in order to estimate this quantum state classically, which introduces some noise into my solution and thereby complicates the convergence analysis that you want to carry out if you want to achieve the state-of-the-art iteration complexity. Now, you can actually modify the Newton system in order to handle the noise that's introduced by using quantum subroutines to obtain the Newton step. But the challenge is that the speedups here aren't very convincing because by using a QLSA, your runtime depends on a condition number bound for the Newton linear systems that arise over the run of the algorithm, which is unfortunately blowing up to infinity as you approach optimality. An important step in overcoming this issue with quantum algorithms was made by Simon Appers and Sander Gribling, who gave a quantum interior point method that was QLSA free and actually achieved some speedups for the tall regime where n, the number of constraints, is much larger than n, the number of variables. But taking a step back and sort of reassessing where we stand, quantum interior point methods, the speedups that they do exhibit, be it polynomial speedups or n-to-n, are largely dependent on some pretty strong assumptions regarding the access that we have to the data. In particular, they're typically assuming access to quantum random access memory. And going back and forth in terms of this QLSA approach between quantum state tomography and the quantum linear systems algorithm, you end up picking up a lot of overhead by doing this sort of classical to quantum conversion. And in fact, if you really think about it more broadly to date, quantum approaches for quantizing the interior point framework have basically sought to accelerate one step of the interior point algorithm. And thereby, it should be unsurprising that they cannot reduce the iteration complexity in general. This is also reinforced by some empirical resource analysis that was carried out by a group at AWS and Goldman Sachs, who looked at the application of the quantum interior point method to solving Markowitz portfolio problems. They looked at a problem in particular with 100 assets that would take seconds to solve on the laptop I'm using to present this talk, and showed that the T-gate counts that they were estimating would roughly account to a quantum computer requiring roughly 1 million years to solve the same problem. So this begs the natural question whether or not there's a more naturally quantum way to accelerate the IPM framework. And in particular, we want a sort of white box quantum input model. It doesn't require so many uses of these, or iterative uses of these very intricate subroutines. And of course, the overarching goal is to try to achieve an end-to-end speedup over the classical IPM. What we're going to talk about today is a way that you can take the central conceit of an interior point method, which is tracing this analytic curve known as the central path to the task of quantum simulation. And that by following the recipe that we sort of spell out here today, you can solve a linear optimization problem involving n constraints and n variables to a given precision in time that's sublinear in these quantities and has linear dependence on the number in the sparsity pattern of your constraint matrix and the scale invariant error parameter. This runtime is basically going to imply that there does exist polynomial speedups in m and n over all existing approaches under some mild assumptions regarding the sparsity of the input matrix. And crucially, no QRAM will be required. All right, so just to take a quick step back, primal and dual LPs. The primal problem is the problem I showed on the very first slide, and it is well known that every primal linear optimization problem admits a dual problem, which provides the best possible lower bound on the optimal objective value of the primal. Under some mild conditions that are always going to hold in this talk, the objective values of these two problems are in fact equal, and this is a phenomenon known as strong duality. So if I introduce some slack variables for each of the constraints in the primal and each of the constraints in the dual, I can rewrite these problems in what is known as standard form. And I have a very straightforward characterization for the set of optimal solutions for the primal and dual problems. Basically, it's the set of tuples that satisfy primal feasibility, dual feasibility, and a complementary slackness condition. And if you look at the complementary slackness condition, you'll note that it's nonlinear, and this is what intrinsically separates linear optimization from, say, solving a linear system of equations. While I'd love to be able to say sample from this set or close to this set, I have no actual recipe for doing so. And so we need some additional tools. Basically, what we're going to do is relax the complementarity problem element-wise. So instead of having this inner product condition, I've basically taken the Hadamard product of the primal with its associated slack and the dual variable with its associated slack and relaxed them to being some non-zero but positive value mu. If we look at the set of solutions to this perturbed KKT system, this gives rise to what's known as the central path, which is uniquely determined by my initial point and extends analytically from that point to the optimal set. An analogy I like to use when particularly there's more physicists in the audience is you can think about mu as sort of like a temperature setting in an annealing algorithm, right? So when I have a high value of mu, I have more freedom to explore the feasible region, looking at lower quality solutions, because this mu is basically going to capture something like the duality gap. As I reduce mu and cool the system, I have to concentrate on higher quality solutions that are reducing the duality gap. And as I go all the way to 0, I get to the optimal set. So I don't know if I've said 1,000 words, but here's a picture. Basically, I have a feasible region here for an LP. For now, I'm going to assume access to a point lying strictly in the interior of this feasible region. And what I know from the theory is that the central path is uniquely determined by this point, extends analytically to the optimal set. But even though I've just perturbed the KKT optimality conditions, they're still nonlinear. So what I do is take a sequence of local linearizations or Newton steps, trying to stay as close to the path as possible while progressing towards the optimal set. In the worst case, I'm going to need something like square root of var theta log 1 over epsilon many Newton steps in order to reach an epsilon precise solution, where var theta can be taken to be the minimum of m and n. And I've sort of completely missed how to actually get this feasible point, right? So we know that the interior point method has to be initialized to a strictly feasible point, but of course, actually obtaining a strictly feasible point is just as hard as solving your original problem to optimality. And so a standard technique from the classical literature on IPMs is to use what's known as the self-dual embedding technique to compose the primal and dual problems into a single, slightly larger problem that always admits a strictly feasible solution. So I've given the actual formulation for the self-dual model here. And the reason why we say it's self-dual is because if you tried to actually go ahead and derive the dual of this problem, you're going to get it back exactly the primal problem, because this matrix M that I've defined in the previous slide is skew-symmetric. So if I define my slack variable associated to any primal solution Z, this mz plus q quantity, then what you can show is that the all ones vector is strictly feasible for this self-dual problem, and its associated slack is the all ones vector as well. This means that we always have a trivial starting point to initialize our algorithm, and the quality of the duality gap is also not too poor. Another interesting feature about this formulation of the problem is that it admits a so-called linear complementarity expression, meaning that you can reduce feasibility to element-wise non-negativity of the primal variable and its associated slack. So using this notion of optimality in the optimal set for the self-dual problem, I can characterize the central path, which is the set of all points Z and their associated slack that satisfy this element-wise complementarity condition and are also element-wise non-negative. I also know that the central path is unique, and there's a simple characterization given here, which is the set of so-called mu centers. Now, as I mentioned earlier, actual IPMs don't actually stay on the path, they just simply stay close to the path. And in order to characterize closeness, I need a notion of a neighborhood of the path, which we're simply just going to define as all of the points that are close in L2 distance to their mu center. And with that, I think we have pretty much all of the ingredients required for our quantum algorithm, so I'll pass everything over to Jiaqi.
Thanks, Brandon. So now I'm going to talk about the actual quantum part, quantum algorithm of our design. So let's go back to this complementarity definition of central path, where we use a set of quadratic equations to characterize the central path. Here, this is quadratic because S of Z is a linear function of Z, and we have this Hadamard product. So, and this mu is the central path parameter. So now we define a new function which we call f of mu. This is a function of Z, where you can imagine Z to be points in the positive orthant. And this function mu, f of mu is defined to be the violation of this set of nonlinear equations. So the larger the function value is, the further the point of Z is getting away from the central path. So basically, this is like a score function which indicates how close or how good we are to approximate the central path. Here are a few properties of this central path function, f of mu. For fixed mu, there should be only one unique global minimizer of this function in the positive orthant because of the uniqueness of the central path. And the minimizer of the f function at mu equals to 1 is the all one vector, which we know that's the starting point because of the self-dual embedding model. So here's our approach. Because we want to trace the zeros of this function f of mu for different choices or values of mu, and we know the starting point for mu equals to 1, and we want to decrease the mu values. And this somehow give us some sort of like a very similar recipe compared to the so-called adiabatic quantum computing, where we know a starting point. We want to engineer an adiabatic path connecting the starting point to a solution, which in our case are some points on the central path. So now the only remaining ingredient is that we want to design a quantum Hamiltonian, because we want to apply the adiabatic quantum computing idea. We need to design a quantum Hamiltonian that encodes the central path as the ground state, so we can adiabatically evolve this Hamiltonian, and at the same time, we can trace down the central path. So here's our definition, formal definition of this central path Hamiltonian. We consider this Schrödinger operator, the so-called Schrödinger operator. It is a differential operator defined in the real space, acting on functions in the real space. We have this Laplacian part, which represents the kinetic energy of the quantum system, because the Schrödinger operator can be understood as something characterizing a quantum system. And we use this f of mu function as the potential field. So here we introduce this h parameter here because we want to stay close to the zeros or minimizers of this f of mu function. And when h is small, sufficiently small, we actually have theoretical results to characterize both the ground states and the spectrum gap of this Schrödinger operator, which are necessary if we want to get a more rigorous analysis of the adiabatic quantum algorithm. So here are some of the results that we borrow from like functional analysis. This is called the harmonic approximation theory of Schrödinger operators in the semi-classical regime. So the first idea is that we only care about the zeros or minimizers of this function f of mu, And in this case, we know it's going to be the analytical center z of mu. We get the second-order Taylor expansion of the function f of mu at z of mu. This gives us a quadratic polynomial. And then we plug this back into our quantum central path Hamiltonian. Now we call this new operator h of tilde, which has the same kinetic energy with the scaling in terms of h. And also we plug in the second-order Taylor expansion of the function. And by some well-established results in function analysis, both the spectrum and the eigenvectors of the original central path operators can be approximated by this kind of Taylor expansion, the second-order expansion of the operator, which now is a quantum harmonic oscillator. And here are some of the more detailed results. Because this is a quantum harmonic oscillator, we can explicitly write down the ground state of this Hamiltonian. Now this ground state corresponds to a Gaussian distribution, a Gaussian state, with this known mean, which is the mu center, z of mu, the point on the central path, and with the known covariance matrix, which is given by the Hessian of this function f of mu at this central path. And also the spectrum gap of this operator is known because we are now looking at the quantum harmonic oscillator. This is both basically h times the square root of lambda of 0, where lambda of 0 is the smallest eigenvalue of the Hessian matrix. So now the idea is that we have a quantum Hamiltonian which encodes the central path. We want to adiabatically evolve this quantum Hamiltonian so that, and also we know the starting point, which is some sort of Gaussian vectors centered at the all1 vector. We can just evolve this quantum Hamiltonian so that the ground state of the quantum system is going to evolve precisely following the central path. And here is a numerical demonstration of this whole idea, where we plot both the ground states and also the probability distribution corresponding to the ground states for different choices of mu, where we illustrate with a two-dimensional system. And here the central path is illustrated with this white dashed line. As you can see, when we decrease the value of mu, this whip packet is getting more and more picked along the central path, and itself is tracing down the central path. So for a very small value of mu, we're going to get a very picked delta-like distribution concentrated on the boundary of the central path, which will give us approximate solutions. And to precisely tracking down the central path, we need to have a more like controlled choice of this parameter h, because this controls basically the tail or the variance of this Gaussian distribution. And here we prove a proposition which says that by choosing this h to be linear in terms of the cube of mu, where mu is the central path parameter, and also inverse proportional to R1 and R infinity squared, where R1 is the L1 norm of the solution, R infinity is the infinity norm of the solution, we can make sure that with a very high chance, the ground state of the quantum Schrodinger operator is going to concentrate it near the so-called N2 neighborhood of the central path. Basically, that says it's getting very close to the central path. And also, our previous proposition was proven by looking at the exactly the ground state of the quantum harmonic oscillator. But in fact, we need to actually pay attention to the true ground state. So in this case, we make an extra assumption, because we know the tail of the ground state is exponentially decay. So we assume that all the probability mass is concentrated in this ball. And this ball is completely contained in this N2 neighborhood of the central path. So it turned out that we have this very rigorous characterization of the probability distribution. And this is a pseudocode of our algorithm, where we basically initialize the state at the O1 vector, a Gaussian state, and then evolve the system. And then at the end, we measure the quantum state, which is equivalent to sampling a point from the picked Gaussian-like distribution. And we get an approximate solution. And this is our complexity result. By choosing the edge, as we discussed before, we can have this kind of query complexity, which is square root of the effective dimension, m plus n, and linear in R1 over epsilon. This is strictly better than previous known first-order method, quantum first-order methods. And by plugging in the gate complexity for this query function f of mu, which means we pay an extra cost linear in the number of zeros in the matrix A, we get the overall gate complexity of this quantum algorithm. So a few concluding remarks. We propose a new quantum algorithm for linear optimization, where we introduce these ideas using Hamiltonian simulation. And this allows us to solve this problem without explicitly using of QRAM or other sophisticated input models. And we can get an end-to-end quantum speedup based on patterns and knowledge of the matrix A. For future works, we probably want to look at if we can further improve the parameter dependence in terms of 1 over epsilon, because now it's still like linear. And also, we want to discuss about like what's the actual cost of implementing this algorithm, as well as if we can generalize this kind of idea to other types of optimization problems, such as semi-definite programming and also second-order conic programming. Okay, I think that's all. Thank you so much.
Thanks for the talk. So am I right in understanding that there's like 2 steps of optimization here? One step is optimizing to be close to the central path, and then the central path is itself an optimization to get to the solution? Okay.
Yeah, that's the correct understanding. Yep.
Thank you. Just clarifying.
Yep.
So I'm just I'm just curious in practice, what kind of application problems would amend themselves to wanting to use a quantum computer to solve a linear program, since you know, in general, solving linear programs is pretty approachable computationally, I would think. So I'm kind of curious, what are the application problems that would admit, you know, wanting to use a quantum computer?
Yeah, maybe I could say a few words on this. So at the end of the day, even though interior point methods are the best performing algorithms, as I mentioned, you're still solving a linear system of equations. And so once you start to look at problems with, say, 1 million variables, you're paying cost 10, n to the 3, basically, or 1 million cubed at each iteration. And so these algorithms are really much more amenable at that small to medium scale. There's also first-order methods nowadays that, like PDLP, which is something that folks at Google have been working on, which is a first-order method that can solve much larger scale problems than, say, an interior point method. But yeah, the real devil is in scale, I would say. So even though these algorithms perform great in practice, there's still a certain threshold where they begin to fail.
I also want to add a bit to the question, because I think theoretically speaking, this is like a precursor to a series of other follow-up works. Because as you can see here, our structure does not necessarily depend on only linear optimization, but actually this complementarity and the violation of complementarity is actually the source of our central path Hamiltonian. And this structure is pretty prevalent and ubiquitous in optimization, including semi-definite programming, which I believe is not regarded as a super well-solved problem, even in practice.
Hi, so I'm wondering, you use adiabatic quantum evolution to that's the ground state of a Hamiltonian to converge to like the end of the central path. But if the landscape function seems quite convex, so I'm wondering if it's possible to use to make it faster. Like you don't need to be even adiabatic; you can move it faster.
Yeah, I mean, we would love to do something faster. I would say right now the way we view this is that adiabatic theorem is one way to prove convergence. And speaking as someone who comes from classical optimization as a background and is getting into quantum since I was in my PhD, I think like designing quantum algorithms, especially end-to-end quantum algorithms for classical problems, we need to identify better tools maybe. Because right now the tools that we are using are coming from physics and maybe weren't necessarily ever thought of as being a tool for solving linear optimization problems, let's say. But I think it's encouraging at the end of the day that we have a runtime using the adiabatic theorem that is competitive with a state-of-the-art algorithm that has been intensely studied for 40 years, whereas we're putting together tools from different fields that maybe with more intense study could be dramatically improved.
Okay, thank you.
All right, let's thank our speakers once more.